Hello and welcome back to once again another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and welcome to episode 12, I believe.
Yep.
And today we're going to be talking just about some astronomy and astrophysics facts about the universe. And if you guys can notice, I indeed have got a brand new microphone, which is making me sound so good.
Yeah, it's much better than the Apple earbuds that you were using before.
So much better.
Awesome. So let's get started from the very beginning. And by that I mean the Big Bang, or what is also known as the beginning of the universe theory. Because we can't actually prove it, but it is very, very probable that it happened.
It is simply the most common or used theory in today's universe because it's the most conclusive. So the Big Bang Theory, for those who don't know, I think everyone might know who's listening to this podcast, but a very interesting thing about the Big Bang, even though the name suggests bang, it wasn't actually much of an explosion as it was of an expansion, because, or at least how we model the early universe, we model it using a point particle or a singularity, known as the initial singularity, that had energy fluctuations within it. These fluctuations then formed or forced this singularity to therefore expand into the universe we know today.
I was reading a book on like there was one chapter on the Big Bang, and there was a theory about antimatter and anti-gravity, and basically, and the theory was that like antimatter could only exist in like high stress situations, like high temperature, high pressure, high density. And basically when the Big Bang occurred, there was enough antimatter in the universe, which was like very, very small at the time, to expand the universe and to keep it accelerating for well, it's impossible to know for how long, but for a very long time. But shortly after the Big Bang occurred, all the antimatter, or most of it in the universe, just dissipated because of the evolving conditions of the universe.
And also one interesting thing that I should say, I should point out what you said. So the interesting thing about antimatter is that when the universe was created, there should have been equal counts matter and equal counts antimatter, right? It makes sense. However, what we see in the universe today, or at least what we can observe, we do not see that whatsoever. We just see mainly amounts of matter. And that's known as baryon asymmetry. It's this theory that really no one has been able to figure out an answer for why, but it just happens that antimatter, for some reason that's unexplainable as of right now, just doesn't exist. Or if it does, as you said, it exists only in extreme conditions. But the fact of the matter is, if the universe did expand, and when the particles and quarks were being created, there should have been equal parts matter and equal parts antimatter. But that just didn't happen. And that's this huge theory, and I would definitely recommend searching up baryon asymmetry just to search up more about this really interesting fact about, why the universe is just not equal.
And here's a question for you, Ray. Do you think that the universe is symmetrical on very large scales?
When you say symmetrical, what do you mean?
Yeah, so when you zoom in, right, to, let's say, our solar system, obviously there's no symmetry.
Yes.
Right? And then we zoom out to our galaxy, still no symmetry there. But I'm talking about massive cosmic superstructures in the universe. If you zoom out to basically have like a God's eye view on the universe, do you think it would be symmetrical on every aspect of the word?
Well, technically, galaxies by themselves can also, like spiral galaxies especially, well, it kind of depends on also how you're defining symmetrical. If you mean like, circulatory, symmetrical, stuff like that, then I guess a galaxy could also be thought it that way, right?
I'm talking about like kind of like a crystalline structure, like it's like a snowflake, like it's just so perfect that you need to zoom in incredibly, or an incredible amount, to see any type of asymmetry that we see on our level of existence, because we are very small yet very big. if you know what I mean.
Exactly. Yeah, so the interesting thing about that is that in small scales, yeah, there really doesn't exist much symmetry because we can't see it. But then we also have to differentiate between the observable universe and what the universe actually is, right? Because what many people think is all we see is what's there, but that's just not true. Because as time passes on, light from distant galaxies that we have never seen before, that is still traveling towards us, light from there hits us as time moves on. So as time goes further and further, our observable universe increases, right?
That can also be explained by this is a Galilean theory, I think, okay? And he postulates that the fabric of space-time between 2 points in the universe, because the universe is expanding, the further away that the 2 points are, the faster that space-time is expanding between them. So there are points in the universe that are so far away from each other that space-time is expanding, close to the speed of light. And so light will basically never reach those 2 points mutually.
That's a pretty crazy theory.
Basically, what this is trying to say is that, like, every second that we live, more and more points in the universe are getting too far away from us for their light to eventually reach us. And so
it can be that our observable universe just has a restriction, is pretty much what you're saying. Right?
There's like a boundary layer where once it's kind of like the event horizon, but the opposite, right? Once you cross that boundary, you will just never be able to make contact with the Earth ever again.
Yeah, I know. That's a pretty sad way to think about it. But but also remember, when we talk about the observable universe, we're kind of centering ourselves in it. So like the Earth is kind of like the middle or the center point of this circle, this imaginary observable universe circle.
What's pretty funny is that to understand basically the inner workings of our solar system, we have to place ourselves off axis, basically, of the center, right? We need to put the sun in the middle, which seemed very counterintuitive until we started seeing things like retrograde, which we'll get into in a bit. But then once we start talking about scales like the observable universe, it actually makes more sense to put the Earth in the center of it, because right now we don't know that, if you go straight in one direction and straight in the other direction, or I guess what I'm trying to say is that there's no definite middle point in the universe. And so making the middle point the Earth is the only thing that makes sense for us, because, well, obviously we're on the Earth. So
and the thing is, we don't even know truly how big the universe is. That's the thing. Like, it can be literally infinite for all we know, but we will possibly have no idea of ever finding out if the acceleration of the universe increases to a point where it's close to the speed of light.
Yeah.
And if that does exist, then we're pretty much done for. We have no way of discovering these other galaxies or these other, who knows what's out there, So there's so many things that can be undiscovered because of this problem.
To be honest, I don't think we will ever be able to know the true size of the universe, because people say like, oh, the universe is big. Well, it's big, but it's even bigger than you could ever imagine. Like, getting to the nearest star, going at the speed of Voyager 2 right now, would take us 80,000 years. And that's just to the nearest star.
And that's only 4 light years away.
Right. To get to the nearest galaxy, the nearest galaxy is what, like 2.4 billion light years.
I think so, yeah.
Andromeda, 2.4 billion light years, or, more or less.
That's the closest big galaxy, yeah.
Yeah, and that would take us, more time than we could even imagine, okay?
Exactly.
So one thing that's kind of interesting, I have the Kurzgesagt calendar, right? And one of the months is, I forget the official name, but it's like you put human embryos in a spacecraft and you send them off to another galaxy.
I think I've seen a video on this.
Yeah. When they're
Yeah.
about like 18, 20 years away from their destination, then you fertilize the embryo, and then
I don't know.
by the time they get to their destination, basically they're like 20 years old and they can start their lives, millions of light years away from where they began their journey. And that's basically the only way that we're going to be able to populate the universe in the future. Well, I say that, I say it's the only way we're going to be able to do it, but at the same time, it's kind of like a caveman trying to describe Wi-Fi. It's not exactly in my realm of capabilities to really describe to you how we're going to populate the galaxy, or if that's ever going to happen. But yeah, right now it's our best guess.
Well, the best way, actually, or at least in my mind, and I think actually could be a viable future, are wormholes, Einstein-Rosen bridges. Because wormholes have already been mathematically proven by Albert Einstein and Nathan Rosen, namely the Einstein-Rosen bridge. We can postulate that it could be hypothetically possible that we can create a space-time wormhole, or at least for now, maybe just a space wormhole, because we're still not too sure about the time specifics. But if a wormhole were to exist and we were supposedly somehow to create one, we would obviously need a lot of things that we don't even have right now. The biggest one being, like, not really antimatter, but like negative energy. The reason I'm saying that is because the number one reason a wormhole collapses, or at least mathematically, is because the throat of the wormhole, that means the connection between the two mouths, they collapse. Now, they collapse because of the existence of gravity, right? And the only way to kind of go around that and keep it open is to use something that goes against gravity, such as negative energy. Or, this is a very hypothetical, dark energy. This is actually a theory that I had when like 2-3 years ago, just for fun, when I was just thinking about space and cool things, where we could use, if we can find a viable source of dark energy, because dark energy is expanding the universe, it's accelerating the expansion. Therefore, we can think of it as an anti-gravitational properties, and that's what dark energy entails. So if we somehow can use that energy, we can possibly prop up a wormhole, create it, and who knows, our limits will be limitless,
I saw this funny meme. It's basically like just a random person talking to an astrophysicist, and the random person goes, dark matter is just like made up stuff that you need to explain the motion of galaxies. And then the astrophysicist says, yeah, go do your research. And then the astrophysicist asks his professor, what is dark matter? And he goes, yeah, it's just made up stuff to explain the yeah. Anyways,
because that is in fact true, because when we saw galaxy rotation curves, we started to notice that there was something that was just accelerating the rotation. So, like, we did what all scientists do, just slap on a name and say, this is why it's happening, right?
Yeah.
So dark matter was formed.
So I wanted to talk about something that, if you're not into astronomy or, the orbits of the moon and stuff like that, you might not know. But, sometimes if you look into the sky at night, you will see that the moon is red. And I don't know, maybe you think that it has something to do with like the red colors of like a sunset, something with our atmosphere, which you would actually be right. It is related to that, to why the sky turns red or orange during a sunset. Mm-hmm. But basically, it's called a lunar eclipse. And what happens is that the Earth comes in front of the moon, or comes in between the moon and the sun. So the moon is being completely shaded by the rays of the sun. So you might be asking, well, okay, if it's in the shade or in the shadow of the Earth, then why is it red? So basically, what happens is that the sunlight that basically hits the atmosphere of the Earth on all sides and doesn't touch the Earth, basically. It just runs through our atmosphere straight through. What happens is that it gets diffracted by the particles in the atmosphere and gets diffracted downwards and basically focuses on the moon. So if you like the glass pyramids, when you shed a beam through it and you see all the colors, basically prism. What happens is that the red light gets diffracted the lowest because it has the lowest wavelength.
Largest wavelength.
Yeah. The largest wavelength, the lowest frequency. And the blue light goes upwards because it has the highest frequency and the lowest highest frequency, lowest wavelength.
Well, technically, that process is known as, like how the sky turns blue. Not exactly lunar eclipses, but like how the sky turns blue or red during a sunset, because I know you were mentioning that, is known as Rayleigh scattering. And it's exactly what you just said. It's when the light hits the atmosphere and the particles pretty much diffract it. So especially when the sun is on sunset, because the light has to travel so much longer to reach our atmosphere, because remember, sunset is when we're far away from the sun or like tilted the other way. So the light has to travel a lot longer, which therefore causes the longest wavelength to show, which is like the orange reddish, thing that we can see in the sky.
So what I was going to say is that because the red light gets diffracted downwards, basically you can imagine the light attacking the circumference of the Earth head on. And then when it gets diffracted by the atmosphere, it gets focused because it gets diffracted inwards, right? It gets focused onto the moon. And that's why we see a red orange-ish shift in the color of the moon. So that's what happens. Oh, sorry. I was saying diffraction this whole time. I meant to say refraction.
Oh, really?
Yeah.
Are you sure? It gets refracted?
Yeah.
Oh, wait, that actually does make a lot more sense. Oh, yeah, that actually does make a lot more sense. Yeah, never mind. Yeah. That is true.
One more thing I wanted to say about the moon is, this is just like a little fact, nothing too scientific. If you ever want to know what phase the moon is in, just remember that you can read the phases like a book. So basically, when the moon it's a new moon, right? It's all dark. Then you open from the right to left, like you're opening a book, and then you close the book from right to left, right? So if the moon is illuminated on its right side, it's the first quarter because you're opening the book halfway and it's the first quarter of that phase. Yeah. So that's how you read the moon phases.
Something else really interesting about the moon, it actually is moving away from us every year by about 4 inches every year. And the reason for this is something that I was so interested in early on that I did a lot of research on this, because it's so cool to think that the moon, which, logically speaking, anything in orbit should be coming towards the planetary body. But in this case, the moon is moving away. Now, the reason for that is because of a tidal lock between the moon and the Earth, or a one-way tidal lock. So what that means is, so originally, if you actually see the moon, something really cool, if every night you will be able to see the exact same structures. Now, why is that? That is because the moon does not rotate on its axis, because it is tidally locked with the Earth. That means only one side, one face of the moon shows itself to the Earth. That's why it's called the dark side of the moon, because literally no one has ever seen it in this or many generations before. Because originally when the moon was just created, the moon used to rotate and the Earth used to rotate as well, and both of them used to rotate on their own axes. However, because the Earth's gravitational pull is so much stronger, the moon exhibited what is known as tidal bulging. That means instead of being a spherical shape, which was its original form, it started to bulge a little bit on its equator. And this tidal bulging is what caused one side of the moon, to eternally lock itself to the earth. Now, because this one side is eternally locked to the earth, there's no more energy that the earth can take away from the moon, because the moon has literally given itself up. It's only being taken from the earth on one side. Because of this, there is rotational energy when when the moon rotates or revolves around the earth. And this energy, coupled with the fact that it's tidally locked with the earth, is what causes the moon to move away every year. And because of this, I think in 200 or 500 million years or something, not that we'll ever be there to see it, but in approximately that time, I think the moon will be officially out of the Earth's orbit. Maybe not 500. I think it was something like billion years. I'm not actually sure. It's some huge number.
That's gotta be a funny sight. Like one day the moon just gets smaller and smaller.
No, but the thing is, by that time, the sun would have already expanded to the point where the Earth is destroyed, because the sun is going to be, because the sun is kind of in the middle of its life, and it has approximately, I think, 2 billion years remaining. So at the end of that, then maybe the moon is going to move away at 2 billion years, something like that. Because I know for a fact that it's going to happen around the same time or after the sun has already pretty much engulfed the Earth. So we're not really going to see a spectacular view, but we're going to die seeing it. So at least that's some satisfaction.
So one of the reasons why I mentioned lunar eclipses earlier is because they actually used a lunar eclipse to measure the diameter of the moon. So that's one thing that actually really intrigued me as a child, or I guess, when I was an early teenager. I was wondering, like, how do you even calculate the diameter of the Earth, or the mass of the Earth, or the distance to the moon, or the distance to the sun? Like, no one has ever even been close to the sun. You can't even really imagine how big the sun really is, which is actually, for context, 1 million times bigger in volume than the Earth. Mm-hmm. But yeah, so I was just really intrigued by that. And so after doing some research, I found that Aristarchus, back in the day, when there was a lunar eclipse.
What day? Which year?
I don't even know.
250 BC.
250?
Approximately 250 BC.
Okay, so 250 BC. He's chilling in his mud hut or whatever, and he sees the moon, right? This is during a lunar eclipse. And it's actually, so basically what he did is he measured the moon's angular diameter, which is basically the angle from the Earth projected onto the moon, right? How wide is it in terms of angles, which is not that hard to do, but it's hard to do accurately. But, he found a way to find some approximation. And so he calculated that during a lunar eclipse, the moon moved through the sky 2.5 times more than the moon's angular diameter. And so basically, by comparing that to the Earth's shadow on the moon, which, during a lunar eclipse, the moon is in the Earth's shadow. So, by that time, they already knew the size of the Earth. So by comparing the size of the Earth to the distance the moon traveled and the time it took and, blah, 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 he was actually able to calculate the diameter of the moon, which is actually 2/7 the Earth's diameter. So just an interesting fact.
Yeah, the moon is actually a really cool thing just in general, because also, interesting fact, another one, is that on the 1969 journey of the first man on the moon, they placed a set of retroreflectors on the moon such that, obviously, maybe Parker and I wouldn't be able to do it, but if you had sophisticated technology, you will be able to shoot a laser at these retroreflectors and measure it when the light comes back, right? Because retroreflectors are basically mirrors with obviously more intensive physics, because the point of it is to always give light back in the exact same direction it came in. So that's what retroreflectors do. They're little tiny prisms pretty much that make up this huge mirror. And what you can see from when the light hits, let's say, your photodetector, right? What you can tell is how far the moon is away from us. And this is a very simple, but obviously you need sophisticated equipment experiment.
Don't you just take the speed of light and the time it takes for the signal to come back?
Exactly. That's what I said. Very simple experiment, but you do need sophisticated equipment. You need like a photo detector. You need a laser strong enough to actually go there. And using this, we have found out that, number one, for all those people that don't believe that the moon landing happened,
I was about to say
conclusive proof that there are man-made things on the moon. And therefore, the only explanation for that is that man has been on the moon. And this was installed on 1969.
One thing that I've heard is that people think, like people who don't believe the moon landing happened, they believe that subsequent moon landings after the first one have happened, but just the first one didn't happen.
I think you and I both know someone who believes this.
Who?
I don't know if you know that person. I'm not gonna say it on this podcast, but I'll tell
just tell me after. But I was gonna say the fact that there are man-made objects on the moon doesn't really explain that the first moon landing happened or not. Mm-hmm. But basically, it's documented that they put those reflectors there, so that should be pretty much enough proof. But anyways, there's a lot of proof that you can use to convince yourself that the moon landing actually happened. And at the same time, I'm not going to go too deep into this because it is a waste of our time to explain why the moon landing happened. But all I want to say is that it's easier to literally go to the moon than to fake a moon landing and have nobody like say a word about it. But okay.
There's this really good episode on YouTube of I forgot like the name, but it's from I completely forgot the channel. It's from College something. I'm not too sure. It's like a really funny channel, but like this
College Humor?
Yeah, College Humor, exactly. And they have like this, not this separate channel, but this kind of this playlist where I forgot the guy's name, but this one guy pretty much disproves, things that we think.
Right. I've seen
exactly.
that.
And in this video, he pretty much talks about how faking the moon landing would not only be more expensive, but so much more inefficient than actually simply going to the moon at that time. Obviously, right now, with the technology we have, Photoshop, Video Shop, stuff like that, anyone can pretty much go on the moon if you just add a few special effects. But at that time, in 1969, with the technology we had, to create those images that we saw of those people on the moon would be so much more difficult than, as Parker said, just going on the moon.
Yeah, and the picture that I'm going to add as the thumbnail of this episode is actually the very first picture of the Earth rising from the moon. And
I've seen that picture. It's a beautiful picture.
Yeah, to recreate that picture in 1969 would be, to the detail that it has, to this day. Mm-hmm. It would be very, very difficult,
Also, an interesting thing about the moon, I remember when I was talking about the dark side and how no one's really seen it. The first person to have seen the dark side on the moon. Now, unfortunately, with Apollo 11, whenever we think about, Apollo 11, we think of what? Neil Armstrong, maybe Buzz Aldrin. Someone we never think about, unfortunately, is Michael Collins, who is also a very respectable astronaut, but he had to stay in orbit around the moon and man the control center, or the command pod, pretty much. And what he did, he was the first person in history of humankind to look or see the dark side of the moon. Because while he was waiting for his fellow compadres who were chilling on the surface of the moon, he was taking an orbit around it. While doing so, he obviously passed by the dark side, which is also, as I said, one of the big reasons why Michael Collins is very famous in the astronomy and, physics world, but unfortunately no one really knows him as the third astronaut on Apollo 11.
You're trying to hype up his job as the commander on the spaceship, but any day of my entire life, I would rather be on the moon than orbiting
obviously,
around.
But you have to understand. You have to understand.
Someone had to do it.
Exactly. Someone had to be there. So it was either him or someone else. Someone else would be there instead of him.
I respect it a lot because he, someone had to do it, and I don't know if he was assigned the job or he volunteered to do it, but just being all right there. You're right above
Yeah, I
the
know.
moon,
It's
but
so
you,
sad. Like, just imagine you seeing your friends, you seeing like your best buds going down to
they're
the
doing
moon,
backflips on the moon.
and you're just chilling in your spacecraft.
Yeah.
And also another interesting thing, while he was on the dark side of the moon, because there was not any major communications, he was the loneliest man in the universe at that point.
True.
When he was at the dark side of the moon, because he had no communication, completely dark, and he was all alone. So
That's
I think
incredible.
Vsauce made a video on this, or because I'm remembering it from somewhere. I'm getting a deja vu while saying this, but he was the loneliest man in the universe for that time period when he was in the
Wow.
dark side of the moon. Sad thing to
Alright.
think about, but it's true.
So I wanted to talk about retrograde, but I'm afraid we don't have that
Yeah,
much time
we
left.
don't.
We are coming up on about 31 minutes.
Mhm.
So I know we will definitely have to make a part 2 to the astronomy
100%. There are
episode.
so many things we have to talk about.
Yeah, I absolutely loved this topic.
Yeah.
So yeah, this has been episode 12 of the Math and Physics podcast. I'm your host, Parker.
And I am Ray, and thank you, and see you soon.
See you guys.